Okay, so we'd like to close off our major ideas today by making sure you fully understand the difference between the system of our pipes and the system of the beverage container. We already proved that the velocity does not depend on the radius of the faucet for a beverage container, and we saw that with the pipes, the radius does affect the speed. We know why already that it does not affect this. So let's delve a little more deeply into the pipes and see why the radius affects speed. Okay, so we start with our open beverage container, and we proved that the velocity equaled the square root of 2gh. That means that the exit velocity depends only on the planet and the depth of the fluid. Nothing else mattered. With a lid, then we start to have other things matter. The pressure inside the container and the type of fluid all of a sudden made a difference. We walked our way through this and we saw that the key formula was Newton's second law, that the net force on the fluid in the acceleration zone is what was responsible for speeding it up. We got the net force by looking at the difference in pressure on the two sides of the acceleration zone. We got a mess of a formula, which I'm going to ask you to simplify in your notes. Instead of writing P3 minus the atmosphere, we'll instead just put delta P. So 1/2 the density of the fluid times the difference between their velocities squared, the velocity on one side of the acceleration zone versus the other, is equal to the density of the fluid, the gravitational field, the height, plus the difference in pressure that is applied to the two ends of the fluid. Okay, so the pressure on one end of the fluid is P3, the pressure at the other spot is P2. Okay, so let's go back to this system where we have a pipe with a coupler and then having the pipe go to a smaller pipe. We saw that the fluid sped up. Today I want to make sure it is crystal clear as to what makes this fluid speed up. We already talked about it, and logically it had to speed up to have the flow rate equal the flow rate in both pipes. If we were going to have 5 liters per minute in one pipe and 5 liters per minute in the other, which we need to have because of conservation of matter, the only way to get that to work is to have the fluid moving faster. That is not justification for why it speeds up. Why it speeds up? The only way something can speed up is if there's a net force on it. The net force is taking place inside the acceleration zone. This time the acceleration zone is the reducer. The net force is coming from a difference in pressure. So if we have pressure 2 here and pressure 1 here, those pressures must be different, and believe it or not, pressure 2 must be higher than pressure 1. If we're going to get this thing to speed up, we need high pressure behind it and low pressure in front. So when this thing contracts into a smaller pipe, it actually causes the pressure to drop. A better way of looking at it is to think of when you hit this reducer, it causes a slowdown in the fluid on the left, and that causes the pressure here to get higher. That higher pressure creates a force which pushes the fluid through the acceleration zone. Think of it like when you had a garden hose. When you put your thumb over one end of the garden hose, you created higher pressure inside the hose. That higher pressure is responsible for accelerating the water and making the water move faster. Okay, so we get high velocity on this side and high pressure on this side. We go back to our formula that we had the other day, and we realize that if both pipes are at the same height, that is, the center of the first pipe and the center of the second pipe are at the same level above sea level, we can get rid of this whole term, and we can just write it like this. There is no change in height. So it's just difference in pressure is responsible for the change in speeds. This idea was first discovered by a scientist named Daniel Bernoulli. He's from the Netherlands and he's in the 1700s. He recognized that when you had faster moving fluid, you had lower pressure. He worked out the equation that's very similar to the equation that we have here. So faster moving fluid, lower pressure. Slower moving fluid has the higher pressure, known as Bernoulli's principle. We can see this pressure washer is going to have very high pressure behind the fluid, but once the fluid comes out, it's going to actually create low pressure. When the fluid hits something and stops, that once again will create a higher pressure. But the actual stream of fast moving fluid actually evidences a lower pressure than the pressure inside the hose. We can see this, and I'm going to demonstrate for you now, if we put a beach ball in a stream of fast-moving air, fast-moving fluid. So as the air rushes around the beach ball, the faster that air moves, the lower the pressure is. Over here, we're going to have normal atmospheric pressure, which will be relatively high compared to the pressure in the airstream. This will actually push the ball into the airstream. The ball will get trapped in there because anytime it tries to leave the airstream, the higher pressure on the outside will push it back into the airstream. Okay, so first I'm going to use this vacuum on its normal setting, which is a vacuum, which is going to create low pressure, and it will pull the ball into the vacuum. Again, it's not really pulling the ball down so much as the atmospheric pressure is going to push the ball down. The pressure underneath the ball will be lower, so the downward pressure is greater and the ball will be stuck to the vacuum. Boom. Now we're going to reverse our airflow. So now, instead of the vacuum pulling things down, it's going to blow air out. And you can see how the ball got trapped in the airstream. Let's bring it a little closer. This same idea is responsible for creating some of the lift on an airplane wing. We get faster moving fluid over the top of the wing. That creates low pressure. Slower moving fluid, air actually, under the wing, and that creates a high pressure, which is going to cause a net force up on the plane. So this is one of the things providing lift on the airplane. Okay, so what I'd like to do now is show you how we can use Bernoulli's principle to find the pressure in a pipe, even though the gauge is broken in the pipe. So we have the pressure in one side of the pipe before the coupler, but we do not know the pressure in the other side. So here's what you do. You start on this side. The water's flowing at 3 meters per second. The pressure over here is 321,000 pascals. And the radius is 19.6 centimeters. A very, very big tube. Okay, so what you start with is flow rate. So find the flow rate on this side. You have the radius, you have the velocity. Once you get that flow rate, set it equal to the flow rate over here. You have the radius here. So you should be able to find your velocity. Once you have that velocity, You then find your change in pressure equals 1/2 density of the fluid, velocity 2 squared minus velocity 1 squared. Velocity 2 is the velocity on this side. Velocity 1 would be this 3. The density of the fluid, we're just going to use water, so you could use 1,000. And you find the difference in pressure. So what does this difference in pressure mean? This is the difference in pressure required to accelerate it to the new speed. This fluid is moving faster than it was before. The only way to have that happen is a difference in pressure. So once you have your difference in pressure, you look at your starting pressure and figure out what your ending pressure would have to be to give you that difference in pressure. So I don't want to do it. I'd like you guys to do it and show me you understand what I'm talking about. Okay, so let's summarize. What's the difference between this one and this one? And the key is this one has a constant pressure difference. Regardless of the size of the opening here, the pressure difference between the two sides of the faucet are going to be the same. And we will get the same speed for the fluid regardless of the size of the opening. That is not true over here. As we saw, when this thing is off, we're going to have one pressure in this pipe. And when we cap it off and make it harder for the water to get through, we're going to create more pressure on this side of the pipe, which is going to change the speed of the water coming out. We can see that there's different amounts of pressure because when this thing is on and we turn on our faucet, we get a lot of leakage here. There's a lot of pressure pushing water through the openings in this system. When on the other hand, we take this off and run it again, we do not get as much leakage. There is not as much pressure built up in this part of our system.